Welcome to the NPTEL online certification course on microelectronics devices to circuit. We will be covering this module as basic MOS transistor basics part 2. So, in part 1 what we had looked into was how a MOS, what is basically a MOS device or a MOSFET, and we have seen that in a MOSFET we have, it is basically a 4 terminal device, but typically even if it is using 3 terminal, the source is generally grounded. We apply a drain bias, we also apply a gate bias, and when the gate bias is above a threshold voltage, the channel is formed, and then if you apply a drain bias, a current will flow. We have also seen that that the width, that the total charge which is available is equals to W into COX into VGS minus VTH, which has, this is known as gate overdrive, right. So, higher is the gate overdrive, larger is the charge accumulated, which makes sense also, because higher the value of VGS, we have to subtract threshold, because that means that amount of minimum voltage will be required to form the channel, and excess of that will give you large amount of charge carriers. We have also seen that when you have gate voltage larger than the threshold voltage and your drain bias is 0, means you do not apply any drain bias. Let us suppose I have N plus and have P type substrate, right. I apply a gate bias here, and this gate bias is getting larger than the threshold voltage of the device. So, I told to you that there will be a charge carriers which will be coming here, right. So, you have a large number of electrons which will be free electrons which will be available here, and there will be a depletion thickness here, and there will be also a depletion region here. Fine, we have discussed this point earlier also, that there will be a depletion region here and here. You will ask me from where these electrons are coming. They are being either supplied by the source side, which is generally grounded, or by drain, which is generally, we apply a positive bias in case of an N channel MOSFET. Now, if the charge carriers here are electron, we define this to be as an N MOSFET, right, and if it is a holes which is basically there, then we define that to be as a PMOS, right, P MOSFET or a PMOS. So, in case of N MOSFET, as I discussed with you, gate voltage should be greater than threshold to achieve it, whereas when you are applying a PMOS, it gate voltage mod of that should be greater than equals to threshold voltage of the device, right, which means that this is what we get from the basic configuration or idea. So, but you see that when you do not apply any gate bias, this is perfectly like this, right, it is exactly like straight line, which means that the number of charge carriers per unit area is almost, or the total number of charge carrier is almost constant as you move from source to drain. It is perfectly symmetrical in nature. But as you go on increasing the positive bias, let us suppose you apply a positive bias and you go on increasing it, then you are actually increasing the depletion thickness, because this is this drain to substrate bias here is basically reverse bias, and there, because you are applying a positive voltage here. So, when you go on increasing the positive voltage, the depletion thickness here becomes more and more. So, it was becoming more and more. Thickness of the charge carriers right from source to drain, which was initially like this, right, now becomes like this, right, and this becomes like this. So, your depletion eats away into the channel, and you have reduced and you have carriers which are just moving towards the source drain region. We will see its implication later on, but that is what we see from here. So, what assumptions we take as far as this MOS device is concerned? We assume that it is a, first of all, we assume that it is a gradual channel approximation, and then we assume that charge sheet model. What is gradual channel approximation? Gradual channel approximation tells me that the electric field in the transverse direction is slightly larger as compared to that in the longitudinal direction, right. So, that is one. So, basically a 1D Poisson equation will be enough to solve a gradual channel approximation based design. So, all your long channel devices, MOS devices, you can apply gradual channel approximation, wherein we tell you that the electric field along transverse direction is relatively larger as compared to that along the longitudinal direction. So, if this is x and this is y, then we say Ex is relatively larger as compared to Ey, right, and we can do one dimensional Poisson equation solution to get these values. We also come to what is known as the charge sheet model, which basically tells me that we assume that it is basically a sheet of charge near the silicon dioxide interface, and therefore what is referred to as a charge sheet model, right, which means that it is basically a model which is assuming that it is a sheet of charge, and therefore rather than per unit volume it is basically per unit area that the charge will be collected with. So, we have two major approximations, and the one is known as gradual channel approximation, also referred to as GCA, right, and we have a charge sheet model here. Now, please understand that that you might not have a gradual channel approximation when your channel dimensions are very small. So, if your lengths are very small, right, so it is okay to have, if your length is very large, the electric fields might be low, but if you reduce your channel lengths to very low values, then for the same value of VDD by L, which is the electric field in, let us suppose, the y direction, is very high. Then my basic assumption that Ex is much larger as compared to Ey will not hold good, and therefore both will be approximately equal to each other, and therefore GCA will not hold good. So, GCAs are always holding good or always good when your channel lengths are typically very large in dimensions, right, fine, and that is what we define as channel charge transition. Now, as there is a voltage, now what I do is, we have seen that when we do not apply any drain bias, the length of my, or the thickness of my charge sheet of electron, which is in this case the charge carriers, are almost constant, is exactly constant from source to drain side. It is a thin layer which you see. Now, if I apply a bias, let us see how does the whole scenario change. Now, at any point, so let us suppose I apply a bias VDS. So, I have got this, I have got this, I have got drain, I have got a source region, right, I have got a this and this. I apply a drain bias here, right, VDS. What it will do is, say you apply 1 volt. So, there will be a potential profile from 0 to 1. So, somewhere here will be 0.5, here will be 0.6, here will be 0.2, here will be 0.4, so on and so forth. As a result, at this edge you will have the most reverse bias, is it okay? And as you move towards the source end, the reverse bias starts to reduce, because the value of voltage starts to fall down, right, and therefore reverse bias increases, and therefore the depletion thickness also goes on reducing. So, you will have the maximum voltage thickness potential or depletion thickness near the drain end, and as a result I will just draw for you, right, and so you will have a maximum voltage thickness depletion thickness near the drain end, and you will have let us see, you will have sorry. So, you will have what? You will have largest depletion thickness here, and then as you move towards the drain end, it will become thinner and thinner. So, you will have a largest depletion region here, because the voltage is maximum here. Then we refine Q of x. Q of x is meaning the charge at any point x is equals to W into COx, right, for obvious reasons, into VGS minus VTH minus Vx. Why minus Vx? Because this is the voltage which is formed because of the charge carrier. So, that has to be subtracted. So, where Vx is the channel potential at any point x. So, let us suppose at this point x you have 0.6, 0.6. So, you have to subtract VGS minus VTH minus 0.6. Why 0.6? Because 0.6 is just required to form the depletion region. So, subtract that to get the charge, right, and therefore the current is given by minus W into C oxide into voltage, applied voltage is V, right, by minus W, because of the simple reason that if the reason being that it is an electron, so the charge will be opposite in nature to the flow of electrons, right, where C oxide is the oxide capacitance per unit area of the device, right. And as you can see here from this discussion, that as the value of Vx goes on reducing, the current goes on increasing, and so on and so forth. So, as you make a V larger, where V is the velocity of the charge carriers, it is given as mu into E, where mu is the mobility of the charge carriers, and electric field is minus dVx dx, where V is the voltage at any particular point at this point. So, I can replace this by what? I can replace this by ID equals to this mu, which you see from here, can be brought forward. So, I can write down minus mu W C ox, right, VGS minus VTH minus Vx, right, into dVx dx, fine. Then what do you do? Then let us see how you go about it. You can then transfer dx on this side and let us see how it works out. Now what you do, so you get id equals to therefore minus this thing. So this, there was a minus sign here initially and there was a minus sign here, so that is the reason it has become plus now, right. So you see id therefore is equals to W into COX, which is the oxide capacitance per unit area, multiplied by VGS, gate to source voltage, minus the threshold voltage of the device VTH, minus Vx, right, because Vx is the potential, multiplied by mobility of the charge carriers, and we write dVx dx. Now we are assuming here for all practical purposes mobility of charge carriers to be constant, right. And now this is a bit slightly over assumptions, but for at this stage of your understanding, assuming mobility to be constant is the right approach to find out the current. Now as you can see from this discussion, that how do you define mobility is basically a velocity per unit electric field, that is how you define mobility, right. So constant primarily means that and if you plot for silicon, velocity versus electric field for silicon, it looks something like this, right. So this is the region where V by E is constant. Similarly here is the region where V by E is constant, right. Somewhere here you have a nonlinear mobility profile, so here it is nonlinear, right. But let us assume we are not going to that high electric fields, you are restricting yourself to low electric fields and velocities are small, and therefore I can safely assume that V by E is constant, which is equals to the mobility. You also should know at this stage before we move forward that mobility can also be of two types, one is known as a bulk mobility and another is known as surface mobility. What is surface mobility? See, it is pretty simple to understand. Bulk mobility is when you have silicon, right, and you apply a bias, silicon is doped with say n type material, phosphorus, and you apply a bias and electron is moving through the bulk of silicon, right. It is scattered by the atoms of silicon and so on and so forth, and it reaches to the drain end, and that is known as the bulk mobility. Then velocity by electric field will be the bulk mobility. What is surface mobility? Well, in reality when you talk about MOSFET, as I discussed with you in your previous discussions, that in a MOSFET the electrons will be moving if it is drain source and you apply a drain bias VDS, then the electrons will be moving through this region, right, where this is basically your silicon dioxide and this is your silicon. So they will be moving across silicon dioxide interface. This interface is not very good because you will have large amount of traps, there will be some oxygen atoms which will be dangling and so on and so forth. So there will be heavy scattering, unlike when the electron moves through the bulk, as it moves to the surface the scattering is very heavy. So when the electrons are very close to the interface of silicon dioxide, the mobility still falls down lower and therefore the current falls down, because current is directly proportional to the mobility of the charge carriers, right, as you can see from here, it is directly proportional to mobility and the mobility falls down. When the mobility falls down, the current also falls down, but that is a second order effect which will come later on. At this stage it is sufficient to know that mobility is constant, and this is how you can find the total current going through it. Now by applying the proper boundary conditions, so this is basically a differential equation and we require two boundary conditions to solve it. The first boundary condition is that we assume that at x equals to 0 V0 equals to 0 and VL is equals to L, which means that at this point this is x equals to 0, right, and this is x equals to L. At x equals to 0 the potential is assumed to be 0 and at this point it is assumed to be VDS, right, obviously because I am assuming that the potential drops within the source and the drain region is almost equals to 0, because it is heavily doped, it is having n plus region typically within it, it has got n plus region typically within it, and therefore I would not expect to see a large potential drop in the source and drain region, right, and therefore it is safe to assume that at x equals to 0 you will have potential equals to 0 and at x equals to L you will have potential equals to VDS or drain to source voltage, whatever drain to source voltage you have applied. Now what you do, you take dx cross multiply, so id dx, and you integrate it from 0 to L, right, where L is the length of the length of the transistor, and similarly V is from 0 so when x equals to 0 V was equals to 0, when x equals to L V was equals to VDS, and you get W into COX VGS minus VTH minus Vx mu n into dV, fine. So when you integrate this one, this is straightforward, this becomes, so when you integrate this left hand side, this becomes id into L, right, because 0 to L is nothing. So integral dx 0 to L is nothing but L, right, and therefore that L is going to the denominator. So I get W by L, and this mu is already there, I bring it mu outside, this is COX, and then what I do is this mu n also comes in the front side because it is constant one independent of the value of VDS, and then if you solve integral dV, if you do with respect to VGS minus VTH minus Vx and from 0 to VDS, if you solve this I get this equation here, right, and it is equals to ID equals to mu n W by L Cox VGS minus VTH into VDS square by 2, fine, and this is the value of the current which you see in front of you. Now now you see here quite interestingly that now the drain current is not a linear function of IDS, right. It would have been so had this term would not have been there, then I would have experienced that ID is almost proportional to VDS, and therefore there would have been almost a linear increase. But since there is a presence, right, since there is a presence and you do have a VDS term coming into picture, right, you do have a VDS term coming into picture, which is also VDS here also you have got, right, and you have VDS here also, and this is VDS square, mind you. So what I can safely say is that there will be a nonlinear profile at smaller values of VDS. Let us see how it works out. So if you look at this, basically the previous discussion, this is basically a parabolic equation, and then if you find out del ID del VDS, then you can find out the peak of the parabola, right, and this is what can be calculated by del ID del VDS. So once you differentiate it for various values of VGS. Now if you plot ID versus VDS, right, for various values of increasing VGS. So VGS3 is greater than VGS2 is greater than VGS1, right. If this is true, which means that the gate voltages, as the gate voltage increases, you see the currents are also increasing, and this is very simple because your overdrives are increasing. See, if VGS is higher and higher, this quantity becomes higher and higher, and therefore the current also increases. As you can see, therefore as the gate voltage increases, your this value also increases. Not only that, your del ID del VGS, right, del ID del VGS will del ID del VDS, sorry, we get the drain to source voltage will also show a shift towards right for a higher gate voltage, which means that I will explain to you physically why is it, mathematically let us understand first that once the drain to source, once the gate voltage is higher, right, you require a larger drain voltage to sort of, if you look very carefully from this region, this is the maximum value of current. After this, either the current will fall, according to this equation the current will fall, or it will remain constant, it will never increase for sure, which means the charge carriers have attained its constant value. If this is true, then let us see why is it like physically. Physically, when you have reached the maximum value here, it primarily means that higher the value of VGS, more is the transverse direction electric field, larger will be the number of carriers, and therefore to deplete it you require a larger drain to source voltage. You getting my point? And therefore this pinch off, this is also referred to as a pinch off point, let us suppose this is pinch off point, let us let me give you a term here. This pinch off point goes on increasing, right, as the value of VGS goes on increasing. So higher the value of VGS, more will be the pinch off point, which means that if you see, if you look very carefully, this is the pinch off point which you get, that when you have VGS3, the pinch off, the value of VDS, right, must be equals to VGS3 minus VTH, at which it becomes maximum. And the reason is very simple, I suppose you have understood by this time why is it very simple. The reason it is being simple is that as you make the gate voltage higher and higher, you have now larger number of carriers available, that is the reason the current is higher, but then you therefore have to give a larger drain to source voltage to reverse bias the region and therefore make it depleted, and therefore the value of VDS is also higher. So what we finally get from this overall understanding is that if you plot ID versus VDS, right, at least till the point when you have reached it, you get something like this. We will discuss this point. Let me not draw at this stage anything like this, but let me draw it. So, let me draw like this and we keep it like this, right. As we move VGS higher, right, and you move VGS lower. So, if you this, so if you plot it, this will be parabola, this will be VGS3 minus VDS, this will be VGS2 minus VTH, and this will be VGS1 minus VTH, where this is the value of VGS1, VGS2, and this is VGS3, fine. So, higher the overdrive, more is the pinch off value of voltage which you see, and that is what you see here at this particular point, that so as you can see from all this discussion, this is the pinch off point occurs. So, now we have found out that the peak occurs at VDS equals to VGS minus VTH, right. So, the peak occurs at VGS minus VTH. Beyond this particular point, right, now if you peak occurs at this, you just feed this value into the previous equation and you automatically get ID to be equals to this much. So, ID max is mu n C oxide, right, by 2 into W by L into VGS minus VTH whole square. And as you can see here, this is actually independent of VDS. So, this is independent of VDS. As you can see, therefore this region is defined as the saturation region. So, we have saturated. So, current is constant independent of the value of VDS which you see, right, and therefore it is constant for all larger values of VDS. With this knowledge, let me come to 3 important characteristics of so this gives me, so what we have discussed till now is that we have discussed the IV characteristics of the device, and we have seen that if current versus voltage is plotted for a fixed value of Vg, right, if this is what is plotted, then we get almost like this profile with us, right, and then almost get saturation region, this is the saturation region and this is the linear region and so on and so forth. So, at this point the device behaves as a constant current source, this point it starts to behave like a resistor, right, and the value of resistance will go on changing as you move from this to this to this. So, higher the overdrive, lower is the resistance. I think it is clear to you why is it like that, because higher the value of resistance, higher the value of the overdrive, more will be the charge, less will be the resistance, right, and therefore this suppose this is on resistance 3, this is R on 2 and this is R on 1, then R on 3 will be smaller than R on 2, smaller than R on 1, right, because the slope is going on increasing as we move ahead, and therefore the resistance is falling down because it is inverse of the slope which we are trying to find out. With this knowledge, we have actually understood the IV or the current versus voltage characteristics of the device, and we have understood the basic fundamental principles of current versus voltage. Now, what we will do is that we will fix the value of VDS and we will vary VGS and see how does my current change, right. So, that is what we are next going to do, and that is known as the transfer characteristics, right, and that is known as transfer characteristics. So, what is the meaning of transfer? It is basically ID, this is ID versus VGS. We will not go into details of this one, I will make it very simple for you to understand, and we will discuss further than this. See, as I discussed with you that when the gate voltage is much smaller than threshold voltage, the device will be in the off state because the threshold voltage, because there are no large number of charge carriers available in the device, and as a result the device will be considered off state. When the gate voltage crosses the threshold voltage, you will have large number of charge carriers at the silicon dioxide interface, and as a result you will have an on state available with you. Typically, if you look at this graph here, we define this to be as the whenever the gate voltage, so this is my threshold voltage, whenever my gate voltage crosses the threshold voltage VTH, right, I can get when this is my threshold voltage, I am sorry, this is my threshold voltage. Whenever my gate voltage crosses the threshold voltage on the right hand side, I get a moderate inversion. Whenever my gate voltage crosses twice VTH or large values, I get strong inversion, and anything smaller than this we get anything gate voltage smaller than the gate voltage on the threshold voltage, we define that to be as a weak inversion. So, we have three points of notation, one is known as a weak inversion, one is known as moderate inversion, and we have a strong inversion. Strong inversion primarily means that inversion means it has become it is just becoming n type and it was initially p type. Strong inversion means if it is becoming twice. So, let us suppose you had a p type substrate where the number of holes were 100, right. Now, what you do, you go on adding, you apply a negative bias. So, electrons are being pulled, they are recombining, and the holes are fully removed, fully depleted. So, there are no holes now, you have only depletion available. Now, what you do, you still go on increasing the gate voltage, more number of electrons are pulled there and it crosses equal to 100, then we define it to be inversion. So, now what has happened is, as many holes were initially present, that many number of electrons are now present, right. If it is almost double of that electron, we define that to be as a strong inversion, right. So, I have a weak inversion, moderate inversion and strong inversion. We define a new term here, and that is known as a subthreshold slope, a very important term in both analog as well as in digital world, especially in digital world where switching is to be done. See, what happens is that though we presume that our gate voltage is equal to threshold voltage is the transition point between on and off state, in reality this is not true, which means that even when the gate voltage is even just smaller than threshold voltage, the device is not fully off, right. The device is not fully off, which means that there are still some charge carriers left which has not been removed, and therefore, we define that region to be as the subthreshold region. Subthreshold means just smaller than threshold, right. In that case we define a term known as S, also known as subthreshold slope, as the amount of gate voltage required to change the drain current by at least 1 decade, which means that, let us suppose your threshold voltage was 1 volt, right. You applied a gate voltage and the gate voltage is approximately equals to 1 volt. Now, what subthreshold slope tells me is that, and at when the gate voltage was 1 volt, let us suppose, right, when we get 1 volt, the drain current which was flowing was, let us suppose, 1 milliamp, just for the information sake. Now, what I do, I decrease the gate voltage by say 60 millivolts, right. And if then the ID value, if this gate voltage reduces by 60 millivolt, if ID drops by 1 decade means from 1 milli is 1 into 10 to the power minus 3 and it drops to 1 into 10 to the power minus 4, 1 decade drop in current, and if to do that, if I require, let us suppose, 60 millivolts of gate voltage change, then we define 60 millivolt to be as the subthreshold slope, and it is given, and the unit is given as 60 millivolt per decade. So, for every 1 decade fall in the current, drain current, the amount of gate voltage which is supposed to be changed in order to bring that change of the drain current is defined as my subthreshold slope. Smaller the value, faster is your change. I hope you understand. Let us suppose I have a device which gives me 20 millivolt per decade. It means that I have to only apply a 20 millivolt gate voltage change in order to 1 decade drop. So, switching is faster. So, subthreshold slope is basically means that it is switching is faster. Lower the value, lower is the switching. So, if subthreshold slope is 90 millivolt per decade and I have a design which is basically 60 millivolt per decade, then 90 millivolt per decade, then 60 millivolt per decade has got a much faster switching from on to off and off to on as compared to 90 millivolt per decade, right. The conventional limit for subthreshold slope is 60 millivolt per decade, that is a conventional limit at T equals to 300 Kelvin. We define this to be as the conventional voltage. With this knowledge, let me recapitulate the basic equations which you have to remember from next time onwards to make it easier for you to understand. The first thing in the saturation region, the drain current is given by ID max, and that is the maximum current is given as mu n C oxide W by 2L into VGS minus VTH whole square, which means that if your VGS minus VTH is doubled, your current will be becoming almost 4 times with you, and that is one of the major. But here if you see clearly, it is independent of VDS. So, ID is independent of VDS, primarily meaning that ID is almost constant, right. It is almost constant independent of VDS. What is the condition for saturation? The condition for saturation is this one, which is VDS should be greater than or equals to VGS minus VTH. Very important term from digital as well as analog point of view, and we should know what is the condition for the onset of saturation. For onset of saturation, VDS should be greater than or equals to VGS minus VTH, which means that drain to source voltage should be larger than the overdrive of the device. In the linear region, we define this as my drain current source. As I told to you, if you are let me say that VDS is very small value, then VDS square will be still smaller, and I can neglect this, and then I can have ID proportional to VDS. That is the linear region of operation, right. So, whenever you have linear region of operation is this one, right, when your VDS is very small, at that place VDS square will be also. So, if VDS is a 0.2 square is 0.04, right. So, 0.04 is very small quantity, I can afford to neglect it, but anything larger than 1, for example, say 0.3 you use 0.3 into 0.9, it will be also very small. So, for small values of VDS, small VDS, this is almost linear because ID is directly proportional to VDS. As you move your VDS slightly higher than 1 and makes it, this non-linearity comes into picture, and you do have a non-linear region here at till how much point, till VDS equals to VGS minus VTH, the onset of saturation. After this it becomes almost straight line. So, I have always saturation, non-linear and exactly linear in dimensions, right. When VDS is much smaller than 2 times VGS minus VTH, the on resistance offered by the device is given by this formula, that R on is equals to 1 by mu n W by L Cox VGS minus VTH, right, and this gives you a small R on in this case. So, with this, let me recapitulate what we did. We have also understood that it is basically a voltage controlled switch MOS device. Who is controlling? The gate voltage is controlling it as a switch. So, I can apply a gate voltage larger than threshold to switch it on, less than threshold to switch it off. It is also acting as a voltage variable resistor, because if you see, as I discussed with you, for a lower value of VGS in the linear region, when lower value of VGS R on is large, and as you increase the value of VGS R on reduces. So, I can use it as a voltage variable resistor as in JFET. Now, typically NMOSFETs and PMOSFETs can be fabricated in a single wafer, and these are the basic building blocks of digital and analog circuits, which is a very simple one. Of course, as I discussed with you, in linear region the transistor acts as resistor, while in saturation it acts as a current source. So, therefore, MOSFET you can see even without understanding anything, it can act as a resistor as well as a current source, right. And therefore, the what is the subthreshold slope? Subthreshold slope is defined as the amount of change in the gate voltage to change 1 decade of drain current, right. Lower the value, better the speed of the device is in switching, right. So, with this we have finished with the basic concepts of MOS device, and we have understood how a MOS device works. We have also understood the basic functionality of a MOS structure, and its usage as a current source as well as a voltage variable resistor. We have understood 3 regions of operation: linear, non-linear and saturation. We have also appreciated what is the value of VDS at which you will have onset of saturation, right, and this will be quite interesting and important for our subsequent studies. I thank you for your patient hearing. We will take up the next issue of MOS devices in the later courses. Thank you.